Welcome, curious minds, to another deep dive. Today, we're plunging into one of chemistry's most elegant and indispensable tools, the periodic table. It's so much more than just a colorful chart on a classroom wall. It's this brilliant organizational system, a kind of chemical Rosetta Stone,
Yeah, absolutely.
It helps us decipher the very building blocks of the universe. It's truly where the entire story of chemistry begins. So what exciting layers of this masterpiece are we peeling back today?
You've hit it perfectly. As the renowned Nobel laureate Glenn T. Seaborg so eloquently put it, the periodic table might just be the single most important concept in all of chemistry.
Wow.
Our mission in this deep dive is to, journey through its incredible origin story, unearth the fundamental principles that govern its structure, and then zoom in on the fascinating, almost magical trends that make the chemical elements behave in such predictable and interconnected ways.
Right.
By the end of our conversation, you'll not only understand how the world is built from these fundamental elements, but critically, why their properties are what they are. It's like a blueprint for the cosmos, and we're going to help you read it.
That's a powerful statement, a blueprint for the cosmos. But if we cast our minds back to, say, the early 1800s, there wasn't really such a blueprint, was there?
No, not at all.
Only about 31 elements were known then, which feels manageable, right? You could probably keep them sorted in your head.
Maybe just about.
But then, fast forward just a few decades to 1865, and that number had more than doubled to 63.
Yeah, a huge jump.
Can you even imagine trying to study each of those individually, plus the almost infinite combinations they formed as compounds? It must have been absolute chaos for chemists.
Absolute unmanageable chaos. You're right. That explosion in discovery was both exhilarating and, frankly, incredibly overwhelming.
I bet.
Scientists were just drowning in this sea of isolated facts about properties, reactions, compounds.
No structure.
Exactly. They desperately needed a systematic framework, a way to bring order to this rapidly accumulating knowledge. The driving force wasn't just to make sense of what they already knew. The truly ambitious goal was to rationalize those known facts and, even more critically, to predict the existence and properties of new elements for future study.
Okay, so prediction was key.
Crucial. Without such a guiding system, chemistry risked remaining just a fragmented collection of observations rather than evolving into the coherent, predictive science it is today. It was a classic example of, information overload pushing the boundaries of human ingenuity.
So this desperate need for order, this push from scientific chaos towards clarity, naturally sparked some incredibly clever, albeit maybe incomplete, early attempts at classification.
Right. People started trying.
One of the very first and most notable was by the German chemist Johann Dobereiner in the early 1800s. What was his brilliant initial idea that started us down this path?
Dobereiner's big idea, which he really solidified by about 1829, revolved around what he called triads.
Triads, like groups of three.
Exactly. He observed that certain groups of three elements shared strikingly similar physical and chemical properties. But here's where it gets really fascinating. The middle element in each of these triads consistently had an atomic weight that was roughly the average of the atomic weights of the other two elements in that triad.
Whoa, okay.
And perhaps even more importantly, its properties were also intermediate between those two. It was a clear hint that there was some underlying numerical relationship connecting these elements.
That sounds like more than just a coincidence. Can you give us an example or two of these triads so we can really visualize the pattern he was seeing?
Of course. A classic triad he identified was lithium, sodium, and potassium.
Okay.
Lithium has an atomic weight of about 7, potassium around 39.
Okay.
Sodium, the middle element, comes in at 23, which is almost exactly the average of 7 and 39.
Right, yeah.
And if you look at their chemical behavior, their reactivity with water, for instance, or the types of compounds they form, they all exhibit a clear family resemblance, with sodium's properties falling squarely between lithium and potassium.
Fascinating. Any others?
Yep. Another example was calcium, atomic weight 40, strontium 88, and barium 137. Again, strontium's atomic weight is very close to the average of calcium and barium. He also saw this with the halogens, chlorine 35.5, bromine 80, and iodine 127.
So the pattern held for a few groups.
It did. While truly groundbreaking for its time, this triad system only worked for a limited number of the known elements. Because of its partial applicability, many of his contemporaries unfortunately dismissed it as, mere coincidence rather than a fundamental principle.
Shame. It sounds like a remarkable insight for its time, even if it was limited. So Dobereiner sparked the idea. What came next on this incredible journey to systematize the elements? Did someone manage to expand on his initial glimmer of order?
Well, the scientific community certainly kept looking. The next significant attempt came from a French geologist, A.E.B. du Champ-Courtois, in 1862.
A geologist.
Yeah.
Interesting.
Yeah, he tried arranging elements by increasing atomic weights on a cylindrical table, sort of a spiral, which he called the telluric helix. It visually showed recurring properties. But it was the English chemist, John Alexander Newlands, in 1865, who made the next big conceptual leap. He proposed what he named the law of octaves.
The law of octaves, that's a really intriguing connection to music. What did he mean by that exactly?
Newlands, like others, arranged the elements in increasing order of their atomic weights. But he noticed a truly striking pattern. Every eighth element, he found, possessed properties remarkably similar to the first element in that sequence.
Ah, like notes in music.
Exactly. He made that explicit analogy to musical octaves, where every eighth note in a scale, like C to the next C, shares a fundamental quality. So if you started with lithium, the eighth element after it, sodium, would indeed behave very similarly, mirroring the properties of the first.
That's such a relatable way to explain it, connecting chemistry to something as universal as music. But was this law of octaves instantly recognized and embraced by the scientific community? Or did it face the same initial skepticism as Dobereiner's triads?
Sadly, no. It wasn't widely accepted at first. Many scientists of the era found the musical analogy a bit, well, whimsical, maybe.
Not serious enough.
Perhaps not serious enough for chemistry at the time. And more critically, his law seemed to hold true only for the lighter elements, specifically up to calcium.
Ah, okay, so it broke down.
Yeah. Beyond calcium, the pattern unfortunately broke down, which led many to dismiss his work. However, the true genius of scientific ideas often takes time to be fully appreciated.
Sure.
Newland's contribution, despite its initial cold reception, was eventually recognized for its profound foresight. He was posthumously awarded the prestigious Davy Medal by the Royal Society in London in 1887.
Wow, so later recognition.
Yes, it shows us that even partially successful ideas, those that hint at a deeper underlying truth, can have enormous long-term impact. He truly set the stage for the major breakthrough that was just around the corner.
So the table was set, so to speak. We had these early hints, these glimmers of a larger design, with Newlands in particular solidifying the idea of periodicity.
That's a repeating pattern.
And this brings us to the two towering figures largely credited with the modern periodic law, Dmitri Mendeleev from Russia and Lothar Meyer from Germany. They were working independently, yet seemed to be racing towards very similar conclusions.
Indeed, their simultaneous work is a classic, fascinating example of scientific discovery being in the air. By 1869, both Mendeleev and Meyer independently proposed that if you arrange elements in increasing order of their atomic weights, you'd reveal striking similarities in physical and chemical properties at regular repeating intervals.
Both hit on periodicity based on atomic weight.
Yes. Lothar Meyer, in particular, was very systematic. He meticulously plotted various physical properties, like atomic volume, melting point, boiling point, against atomic weights.
We made graphs.
Exactly. And what he observed was this beautiful, periodically repeated pattern. Though he also astutely noted that the length of that repeating pattern wasn't always the same, which was a crucial insight. Meyer had actually developed a table of elements as early as 1868 that remarkably resembled the modern periodic table.
Really? Before Mendeleev?
Well, he developed it, but his work wasn't published until after Mendeleev's, which is why Dmitri Mendeleev typically receives the lion's share of the credit and historical spotlight for this monumental achievement. Timing is everything sometimes.
Right. That's a key piece of information. So what was it about Mendeleev's approach that made it so famous, that etched his name into the history books, even if Meyer had a similar table? What was Mendeleev's unique stroke of genius that truly elevated his work?
Mendeleev's approach was not just observant. It was incredibly audacious and confident. He wasn't simply arranging known elements. He was making profound, almost philosophical statements about the very fabric of matter.
Okay.
He was the first to publish the periodic law, stating it as this immutable principle. The properties of the elements are a periodic function of their atomic weights.
He laid it down as a law.
Yes. He then meticulously arranged elements into horizontal rows and vertical columns, ensuring that elements with similar properties precisely aligned in the same vertical column, or group. But what really distinguished Mendeleev's system from Meyer's was its sheer comprehensiveness and his incredible foresight. used a much broader range of physical and chemical properties to classify elements, not just a few physical parameters.
More holistic.
Exactly. He placed particular emphasis on the similarities in the empirical formulas and properties of the compounds that elements formed, especially with oxygen and hydrogen. This holistic view of chemical behavior was a major differentiator.
And he wasn't afraid to challenge the existing data, was he? I mean, for scientists to essentially say, the measurements are wrong, not my theory, that takes an extraordinary amount of conviction.
Precisely. That was truly one of his most audacious and ultimately brilliant moves. He wasn't a slave to the data. He was a master of his theory.
Right.
He recognized that some elements, if strictly placed by their atomic weights, simply didn't fit into his recurring pattern of properties. So rather than abandoning his entire system, he, with remarkable foresight, ignored the atomic weights of certain elements.
Bold move.
Very. He believed, quite correctly, that the measurements themselves might be incorrect, or perhaps that some elements simply had not been discovered yet. He prioritized placing elements with similar properties together.
Like the iodine and tellurium case.
Exactly. That's the classic example. Iodine has a slightly lower atomic weight than tellurium. But Mendeleev placed iodine after tellurium in group 7 because iodine's properties clearly match those of fluorine, chlorine, and bromine in that group. Tellurium's properties, meanwhile, aligned more with oxygen and sulfur in group 6.
So chemistry trumped the numbers.
His chemical intuition trumped the accepted atomic weights. This decision, which seemed counterintuitive at the time, was a testament to his unwavering faith in the periodic principle he had uncovered.
And then the gaps. Leaving empty spaces in his meticulously constructed table, predicting entirely new elements that had never been seen before. That must have felt like an enormous gamble, a real leap of faith.
It wasn't just a gamble, it was an act of scientific prophecy, really, and perhaps the strongest, most compelling evidence of the predictive power of his periodic table.
Because it showed the system worked beyond what was known.
Exactly. His primary aim was always to group similar elements. So when an element didn't fit the pattern, he didn't force it. He proposed that some elements were simply undiscovered. He left several well-defined gaps in his table, most famously for Eka aluminium.
Meaning next to aluminium?
Yes, Eka meaning one in Sanskrit, so one after aluminium, and Eka silicon, one after silicon. But here's the kicker. He didn't just predict their existence. He went a colossal step further.
He described them.
He described their general physical properties and even the properties of their compounds with astonishing accuracy. For Eka aluminium, for instance, he predicted an atomic weight of 68, a density of 5.9 gc-meter, and an oxide formula of Eka Ilos.
Okay, so very specific predictions.
Very specific. Now, imagine the scientific world's reaction when gallium was discovered years later. Its atomic weight was found to be 70, pretty close.
Wow.
Its density 5.94 gc-meter, almost dead on.
Unbelievable.
And its oxide, Gayuros. The match was almost eerie. Similarly, for Eka silicon, he predicted an atomic weight of 72, density 5.5 gc-meters, oxide E oro. When germanium was subsequently discovered, atomic weight 72.6, density 5.36 gc-meter, oxide G oro.
Just incredible confirmation.
These precise predictions and their stunning confirmation cemented his table's fame and convinced the scientific community of its profound significance. It was no longer merely a classification system. It was a powerful roadmap to scientific discovery, a true revelation.
That's an incredible story of scientific vision. Mendeleev created this groundbreaking system, not just organizing the known, but predicting the unknown. Revolutionary for its time. But our modern table, the one we see everywhere today, is founded on a slightly different principle, isn't it?
It is.
What was that critical shift, that new understanding of the atom that led to the modern periodic law and the table's current form?
That takes us into the early 20th century, a time just buzzing with discoveries about the atom's internal structure. While Mendeleev based his law on atomic mass, which was the best available property then, the very notion of a fundamental property shifted.
Something more fundamental than mass.
Exactly. The critical conceptual leap came in 1913 with the English physicist Henry Moseley. He was experimenting with characteristic X-ray spectra emitted by different elements when you bombard them with electrons.
Okay, looking at X-rays.
Yes. And what Moseley discovered was truly monumental. He found that if he plotted the square root of the X-ray frequency versus the atomic number Z of the elements, he got a perfectly straight line.
A linear relation.
A perfect linear relationship. But, and this is crucial, a similar plot against atomic mass did not yield a straight line. It was much messier.
Ah, so atomic number was the key.
This definitively proved that the atomic number, which is essentially the number of protons in an atom's nucleus, is the more fundamental property of an element. It wasn't the atomic mass that truly governed an element's chemical and physical behavior, but its atomic number, Z.
So the modern periodic law is based on atomic number. How does that fundamentally change our understanding of elements and their properties compared to Mendeleev's original formulation based on atomic mass?
It's a profound redefinition of the core principle. The modern periodic law states, the physical and chemical properties of the elements are periodic functions of their atomic numbers.
Simple but deep.
Very deep. This wasn't just a minor correction. It was a deep conceptual refinement. It allowed us to recognize that the periodic law is, at its heart, a direct consequence of the periodic variation in the electronic configurations of atoms.
Ah, the electrons.
Yes. Remember, the atomic number equals the nuclear charge. And in a neutral atom, it also tells us the number of electrons. It is these electron configurations, particularly the arrangement of the outermost, or valence, electrons, that directly dictate an element's physical and chemical properties and how it interacts with other atoms. So the table isn't just about weight or protons, it's really a map of electron arrangements.
And that leads us to the long form of the periodic table, which is so familiar to us today. What are its key features that make it so incredibly convenient and widely used in classrooms and labs worldwide?
The long form of the periodic table is indeed the most intuitive and widely used because it visually represents this electronic configuration basis so well. It organizes elements into horizontal rows, which we call periods.
Rows are periods.
And vertical columns, which are known as groups or families. The real power here is that elements in the same vertical group possess similar outer electronic configurations.
Same column, similar electrons.
Exactly. And as a direct result, they exhibit very similar chemical properties. That's the key link. To ensure global consistency, the International Union of Pure and Applied Chemistry, IUPAC, standardized the group numbering from 1 to 18, left to right.
Okay, 1 to 18.
In total, there are 7 periods, 7 rows. The number of a period directly corresponds to the highest principal quantum number n for the elements within that period. So period 3 elements have their outermost electrons in the N3 shell.
Got it.
The number of elements in each period follows a very specific sequence, reflecting the capacity of the electron shells being filled. The first period contains just 2 elements, the second and third have 8 each, the fourth and fifth have 18, and the sixth period has 32 elements.
2, 8, 8, 18, 18, 32.
Right. The seventh period is still technically incomplete, but theoretically could hold 32 as well. Crucially, to keep the table from becoming awkwardly wide.
Yeah, it would be huge otherwise.
And to maintain its functional structure, the 14 elements from the 6th period, the lanthanoids, and the 14 elements from the 7th period, the actinoids, are placed in separate panels at the bottom. This preserves the table's elegant visual layout while still correctly classifying these inner transition elements.
That structural explanation is super helpful. Now, let's step into the cutting edge of chemistry. What happens when we discover, or more accurately, synthesize incredibly heavy, highly unstable man-made elements with atomic numbers over 100?
The super heavies.
Yeah. How do scientists even go about naming them, especially since I've heard there's been quite a bit of international controversy and competition in the past?
That's a fantastic question, and it perfectly illustrates the competitive and sometimes challenging nature of modern scientific discovery. Historically, the discoverer of a new element traditionally had the honor of suggesting its name, which IUPAC would then officially ratify.
Discoverer gets naming rights.
Traditionally, yes. However, with new elements having very high atomic numbers, they become incredibly unstable, often decaying within fractions of a second.
Gone in a flash.
Pretty much. Sometimes, only a few atoms, literally a handful, are ever obtained, making their synthesis and characterization extraordinarily difficult and requiring incredibly expensive specialized equipment. This intense difficulty, combined with the immense prestige of discovering a new element, led to fierce competition and, inevitably, disputes between different research labs and scientific teams.
Ah, the race to claim it first.
Exactly. Each rushed to claim discovery, leading to these disputes. Host, speaker, speaker. So, if multiple labs were claiming discovery and proposing different names, it must have created quite a mess for the scientific community. Did IUPAC have to step in and impose some rules to bring order to this naming chaos? Absolutely. To avoid precisely these kinds of international naming controversies, for example, both American and Soviet scientists claimed element 104. The Americans proposed Rutherfordium, the Soviets Khrushchevium.
Right, I remember that.
So yes, IUPAC established a systematic provisional nomenclature for elements with atomic numbers greater than 100. This system serves as a temporary placeholder, used until a discovery is fully verified and its name officially recognized and agreed upon by the global scientific community.
A temporary naming system, how does that work?
Under this provisional system, a temporary name is directly derived from the atomic number itself, using specific numerical roots for each digit. Nil for 0, for 1, bi for 2, tri for 3, quad for 4, pent for 5, hex for 6, or 7, octet for 8, and n for 9.
Like Latin or Greek roots?
Pretty much. These roots are strung together in the order of the digits that make up the atomic number, and then the suffix "ium" is added at the end.
Okay, give me an example. Say element 120.
Element 120. So 1 is un, 2 is bi, 0 is nil. String them together, un and bi nil, add ium. Its temporary name would be unbenillium.
Unbenillium, got it. And this symbol?
Just take the first letter of each root, u, a, b, n.
Simple enough.
Once a discovery is fully ratified and unequivocally verified, a permanent name and symbol are bestowed. These permanent names often reflect the country or state where the element was discovered, or they honor a notable scientist, much like Seaborgium, was named in honor of Glenn T. Seaborg for his pioneering work on transuranium elements.
Right, makes sense.
As of today, elements up to 118 have been officially discovered and named, completing the 7th period of the table.
So the modern table is organized by atomic number, which we now know directly links to an element's electronic configuration.
Correct.
How does that crucial link help us classify elements into those familiar blocks, the S, P, D, and F blocks that define their chemical behavior?
The classification into blocks is a beautiful direct consequence of the Aufbau principle.
The building up principle.
Exactly, which in essence dictates the precise order in which electrons fill the various atomic orbitals in an atom. Elements are neatly categorized into these 4 distinct blocks, block B block, D block, and F block, based simply on the type of atomic orbital that receives the last electron added to the atom in its ground state.
So it's all about the last electron's address.
Precisely. This fundamental principle gives us a robust theoretical foundation for the entire periodic classification.
Let's unpack each block for our listeners. Starting with the S block, what are its defining characteristics, and where do we find these elements on the table?
The S-block elements are located on the far left of the periodic table. They include Group 1, known as the alkali metals.
Like sodium, potassium.
Right. They have an outermost electronic configuration of N-Elis, 1 electron in their outermost orbital. And right next to them is Group 2, the alkaline earth metals.
Calcium.
Magnesium. With an NSN configuration, 2 electrons in their outermost orbital. They are all highly reactive metals, characterized by their notably low ionization enthalpies.
Easy to lose electrons.
Very easy. This means they readily lose their outermost electron or two. This strong tendency leads to the formation of 1+ ions for alkali metals and 2+ ions for alkaline earth metals. You'll observe that their metallic character and overall reactivity predictably increase as you descend down any S-block group.
Gets more reactive going down?
Yes. Because of their intense reactivity, you will never find them in their pure elemental form in nature. They always exist as compounds. And generally, they're compounds, with the notable exceptions of lithium and beryllium, which have some covalent character, are predominantly ionic in nature.
Okay, that's this block. What about the P block elements? Where are they situated and what makes them unique, especially with those noble gases at the very end?
The P block elements are found on the right side of the periodic table, spanning from group 13 all the way to group 18.
The whole right side.
Pretty much. Together with the S-block elements, they are broadly referred to as the representative elements, or main group elements. Their outermost electronic configuration ranges progressively from NCERT for group 13 elements up to the highly stable NCERT for group 18.
Filling up the p orbitals.
Exactly. Now, at the very end of each period within this P block, you find the noble gas elements, group 18. They possess a completely filled valence shell configuration of NCERT.
The stable octet.
Right, that stable configuration. All the orbitals in their outermost shell are full. This extreme stability makes it incredibly difficult to either add or remove electrons, which perfectly explains their very low chemical reactivity. They are, chemically inert for the most part.
Happy as they are.
Pretty much. Preceding the noble gases are 2 chemically crucial groups of nonmetals. The halogens of group 17.
With fluorine, chlorine.
And the chalcogens of group 16.
Oxygen, sulfur.
Right. These elements have highly negative electron gain enthalpies.
Meaning they like gaining electrons.
Yes. They release a significant amount of energy when they gain 1 or 2 electrons, respectively, to achieve that highly desirable, stable, noble gas configuration. They are effectively electron-hungry. A key trend within the p-block is that non-metallic character increases as we move from left to right across a period.
More non-metallic to the right.
While metallic character generally increases as you go down a group, this block is truly diverse, showcasing metals, nonmetals, and those fascinating elements in between, the metalloids.
Next, let's move to the D-block elements, which are famously known as the transition elements. They sit in the middle of the table, almost like a bridge, you said.
That's an excellent way to think of them as a bridge. The D-block elements are positioned right in the center of the periodic table, encompassing groups 3 to 12. Their defining characteristic is the filling of their inner d orbitals by electrons.
Filling the N1 orbitals.
Precisely. Their general outer electronic configuration is N1 diels, though there are some interesting exceptions to this general rule, like palladium, which has a 4do 5-das degree configuration.
Always exceptions.
Chemistry loves exceptions. All D-block elements are metals, and they exhibit a fascinating array of properties that distinguish them. They often form beautifully colored ions in solutions.
Like copper sulfate blue.
Exactly. They display variable valency or multiple oxidation states. Many are paramagnetic, meaning they're attracted to magnetic fields, and they are widely used as catalysts in various industrial chemical reactions.
Very useful elements.
Extremely useful. However, it's an important point that elements like zinc, cadmium, and mercury, which have a completely filled N1 d-trans electronic configuration, don't show many of the typical transition element properties.
Because their D shell is full.
Exactly. For instance, they don't generally exhibit variable oxidation states or form colored ions because their orbitals are already full and stable. In a broader sense, the transition metals act as a crucial link, bridging the highly reactive metals of this S block on the left with the less active, more diverse elements found in groups 13 and 14 on the right. Hence their fitting name, transition elements.
And finally, the F block, or inner transition elements. Where do they fit into this grand scheme and what makes them unique, tucked away at the bottom of the table?
The F block elements are those two distinct rows placed separately at the very bottom of the periodic table. These are the lanthanoids.
Top row of the bottom section, right?
Which range from cerium, Z58, to lutetium, Z71, where the 4 orbitals are progressively filled with electrons. And below them, we have the actinoids.
Bottom row.
From thorium, Z90, to lawrencium, Z103, where the 5 orbitals are being filled. Their general outer electronic configuration is typically N1 loop.
Filling the N2O orbitals, that's deep inside.
Exactly. The defining characteristic is that the last electron added to each element in these series is filled into an F orbital, which is a deeper, more shielded orbital. Hence their designation as F-block elements or inner transition elements.
Makes sense. What are they like?
They're all metals, and within each series, the properties of the elements are remarkably similar. This actually makes them quite challenging to separate from each other chemically.
I've heard that.
However, the chemistry of the early actinoids is particularly complex compared to the corresponding lanthanoids, primarily because the actinoid elements can exhibit a much larger number of possible oxidation states. A significant characteristic of all actinoid elements is that they are radioactive.
All of them?
All of them. Many have only been synthesized in minuscule quantities, sometimes even nanograms, through complex nuclear reactions. This means their chemistry is still not fully studied or understood. Any elements after uranium in this series are collectively called transuranium elements.
That's a comprehensive breakdown of the blocks. But given these rules, are there any elements that don't quite fit neatly into these blocks, or perhaps have special cases that challenge the simple classification? It feels like nature always has a few curveballs.
Carrie, you're absolutely right. There are indeed 2 important exceptions that are often discussed because they highlight the interplay between electron configuration and observed properties. The first is helium.
Helium, it sits with the noble gases.
It does. But technically, with an electronic configuration of 1 centifour, helium perfectly fits the definition of an S-block element, as its only electrons are in this orbital.
Ah, right, 1 centisol.
However, it is always positioned with group 18, the p-block noble gases. This placement is entirely justified because its completely filled valence shell, von Sisson-Smock, gives it chemical properties that are identical to other noble gases, extreme stability, and very low reactivity, rather than the reactive metals of the S-block. It behaves like a noble gas, not an alkaline earth metal. So properties win over configuration in this case.
Okay, placement by behavior. What's the other one?
The other notable exception is hydrogen, with only 1 s electron, 1 s, It could theoretically be placed in group 1 alongside the alkali metals, as it can lose that single electron to form a positive ion, H plus NF.
Makes sense.
But uniquely, it can also gain an electron to form H, achieving a stable noble gas arrangement like helium. This makes it resemble the halogens in group 17, which also like to gain one electron.
So it's like both group 1 and group 17.
Exactly. Because of this unique and dual nature, it doesn't quite fit squarely into one family. It's typically placed separately, at the very top of the periodic table. This acknowledges its distinct behavior and prevents it from misleadingly implying strong similarities to either group 1 or group 17, as its chemistry is truly its own thing.
That makes perfect sense. So thinking about where elements go, if we were to discover or synthesize an element with atomic number Z117 or Z120 today, based on everything we've just discussed, where would they slot in? This seems like a great way to test our understanding.
Absolutely. It's an excellent exercise and apply the principles. For an element with atomic number Z117, let's think. We follow the electron filling order. It would be the penultimate element of the 7th period.
Second to last in row 7.
Right. This means it would belong to group 17, placing it directly below tennessine and Ts and making it a halogen.
Another halogen.
Its predicted electronic configuration would be Rn 5 Ts little 777 Terry. See that pound ending?
Yeah, just like fluorine is upon its shell.
Exactly. Just one electron short of that highly stable noble gas configuration. This predicts it would be a highly reactive nonmetal.
Okay. And Z120.
Now, for the element with Z120, following the same logic, it would be the first element in the 8th period. It would start filling the 8th orbital.
A whole new row.
Right. This means it would be placed in group 2, making it an alkaline earth metal sitting below radium. This electronic configuration would be UA Cibosari, meaning it has 2 electrons in its outermost orbital.
Like calcium or magnesium.
Just like them, but in the next period down. This exercise beautifully illustrates how understanding electronic configuration directly dictates an element's placement and, by extension, allows us to predict its general properties even if it hasn't been synthesized yet. It truly is the ultimate predictive power of the modern periodic system.
Absolutely fantastic. Okay, beyond the S, P, D, and F blocks, the periodic table also offers us a quick and intuitive way to differentiate between metals, nonmetals, and those intriguing in-between elements, the metalloids. This is perhaps one of the most fundamental classifications we see. What are the key distinctions in terms of properties that define these categories?
This is indeed a fundamental classification, and it's primarily based on the observable physical and chemical properties of the elements. Metals make up the vast majority, over 78% of all known elements.
Most elements are metals.
Yeah, the vast majority. They are predominantly found on the left side and in the center of the periodic table. Typically, metals are solids at room temperature, though we have notable exceptions like mercury, which is a liquid.
Right, mercury is a famous one.
And gallium and cesium melt at very low temperatures, close to room temp. Metals generally have high melting and boiling points, indicating strong metallic bonding. Critically, they are excellent conductors of both heat and electricity.
Why is that again?
Because their valence electrons are delocalized, meaning they aren't tied to one specific atom, but are free to move throughout the metallic structure, carrying charge or heat energy.
A sea of electrons.
That's the classic description. Furthermore, metals are characterized by their malleability. They can be hammered into thin sheets without breaking, and ductility. They can be drawn into wires. They also possess a characteristic luster. They look shiny.
Okay, clear properties for metals. And how do nonmetals contrast with metals in terms of their properties and their usual location on the table?
Nonmetals are situated on the top right side of the periodic table. In stark contrast to metals, nonmetals are usually found as solids or gases at room temperature. Bromine is a liquid nonmetal exception. They tend to have much lower melting and boiling points, though boron and carbon are notable exceptions with very high melting points.
Diamond and graphite.
Right. They are generally poor conductors of heat and electricity because their electrons are tightly held within localized covalent bonds or on individual atoms. They don't have that sea of mobile electrons. Most solid nonmetals are also brittle, meaning they shatter easily when hammered and are neither malleable nor ductile. They often lack luster.
So pretty much the opposite of metals.
Largely, yes. A crucial observation is that as you move from left to right across any given period, the elements generally shift from exhibiting metallic characteristics to non-metallic characteristics. It's a gradual but significant change across the row.
Given that clear distinction, where do metalloids or semi-metals fit in? Do they represent a blurry line, a kind of transition zone between these two main categories?
Precisely. The transition from metallic to nonmetallic character across the table isn't abrupt. It's a smooth, fascinating gradient. Elements like silicon, germanium, arsenic, antimony, and tellurium are found bordering a distinctive zigzag line on the periodic table.
That staircase line you often see drawn in?
Exactly that staircase. It essentially runs diagonally through the P block. These elements are called metalloids, or semimetals, because they uniquely exhibit properties characteristic of both metals and nonmetals.
The best of both worlds. Or maybe the confusing part of both worlds.
Maybe a bit of both. For instance, they might possess a metallic luster, appearing shiny, but be brittle like nonmetals. Or famously, they might be semiconductors.
Like silicon in computer chips.
Exactly. That's the most famous application. They conduct electricity only under specific conditions or when doped with impurities, unlike true conductors, metals, or insulators, nonmetals. As a general rule, metallic character increases as you go down a group.
Because atoms get bigger, lose electrons easier.
Precisely, due to increasing atomic size and decreasing ionization energy. Conversely, nonmetallic character increases from left to right across a period due to increasing effective nuclear charge and a greater tendency to gain electrons. The metalloids lie in that fascinating, technologically crucial transition zone.
Now for the why. This is where the real deep dive begins. Why do elements exhibit these predictable trends in their physical and chemical properties? We see these patterns in reactivity, size, energy. But what's the scientific reason, the underlying atomic principle behind them? Before we dive into specifics like radius or ionization energy, can you give us a mental model for the core ideas that explain these trends? Like, I hear terms like effective nuclear charge and electron shielding thrown around.
Absolutely. To truly understand why properties change across the periodic table in the way they do, we need to grasp 2, maybe 3 fundamental concepts about atomic structure. Think of the nucleus of an atom with its positive protons as a powerful positive magnet.
Okay, nucleus magnet.
First, nuclear charge is simply how strong that positive magnet is. It's directly related to the number of protons, Z, in the nucleus. The more protons, the stronger the overall pull. Pretty straightforward.
More protons, stronger magnet. Got it.
But electrons aren't alone. They also create a kind of shield or screen around the nucleus. Imagine you're an electron trying to feel the pull of that positive magnet in the center. If there are other electrons between you and the magnet,
they get in the way.
Exactly, they get in the way. They have their own negative charge, so they repel you slightly and partially block or reduce the magnetic pull you experience from the positive nucleus. That's electron shielding or screening. Inner electrons shield the outer electrons.
Okay, inner electrons block the pull for outer electrons?
Right. So the effective nuclear charge, often written as 0 by E20 by 820 by 9010 by E20 by 820 by 91, is how much of that positive nuclear magnet pull the outermost electrons actually feel, after some of it has been blocked or shielded by all the inner electrons. It's the net positive charge experienced by a valence electron. It's always less than the full nuclear charge, except for hydrogen.
The pull the outer electron actually feels.
Precisely. And finally, the principal quantum number n simply tells us which main energy level or shell the outermost electrons are in. Higher n means further from the nucleus. These 3 factors, nuclear charge, pulling power, shielding, blocking effect, and quantum number or distance, are the master keys to unlocking basically all the periodic trends.
That's a perfect foundational explanation. Nuclear charge pulling in, shielding, blocking that pull, and distance making the pull weaker. Got it.
With those concepts in mind, let's start with atomic radius. It sounds simple enough, the size of an atom, but measuring something as tiny and, well, fuzzy as an atom must be incredibly tricky, right? How do scientists even go about estimating it, given those indistinct electron clouds? You're absolutely right. It's incredibly complicated. First, atoms are unbelievably tiny, typically having radii around 1.2 by 10 irradiators. That's 1.2 angstroms, or 120 picometers. Just minuscule.
Hard to even imagine.
Exactly. Second, and perhaps even more challenging, their electron clouds don't have sharp, well-defined boundaries. They are, as you said, fuzzy regions of probability. So we can't precisely measure the size of an individual isolated atom with, a tiny ruler.
Right. No edge to measure to.
Precisely. Instead, what we do is estimate atomic size by measuring the distances between the nuclei of atoms when they are in a combined state, usually bonded together in a molecule or packed together in a crystal.
So we measure the distance between centers of bonded atoms.
Yes. For nonmetallic elements, we typically use what's called covalent radius. This is defined as half the distance between the nuclei of 2 identical atoms that are joined together by a single covalent bond in a molecule. For example, in a chlorine molecule. The bond distance between the two chlorine nuclei is measured to be 198 picometers pm. So half of that 99 pm is taken as the atomic radius, or more specifically, the covalent radius of chlorine.
Okay, half the bond length for nonmetals. What about metal?
For metals, we use metallic radius. This is defined as half the inner nuclear distance separating the metal cores, the nucleus plus inner electrons, in a metallic crystal lattice. For instance, the distance between two adjacent copper atoms in solid copper is 256 pm. Therefore, the metallic radius of copper is assigned a value of 128 pm. These are practical, albeit indirect, estimates that allow us to compare sizes and observe trends reliably.
Okay, so with those measurement methods in mind, what are the clear, predictable trends for atomic radius as we move across a period and down a group in the periodic table? How do Z by E20 by 820 by 910 by 20 by 820 by 820 by 91 and shielding play out?
There are two very distinct and important trends for atomic radius, and they directly relate to those concepts. First, across a period, from left to right, atomic size generally decreases.
Gets smaller going across. Why?
To understand why, remember that within the same period, successive electrons are being added to the same outermost valence shell, same N. However, as we move from left to right, the atomic number, and thus the number of protons in the nucleus, increases by 1 each time. This means the nuclear charge increases. While shielding from inner electrons increases slightly, it doesn't fully counteract the stronger pull from the extra proton. So the effective nuclear charge, 0 by E20 by 820 by 820 by E20 by 820 by 820 by 891, experienced by those outer electrons increases.
Stronger pull on the same shell.
Exactly. This increased effective positive charge in the nucleus pulls the outermost electrons more strongly toward itself, like that magnet getting stronger, effectively shrinking the electron cloud and making the atoms smaller as you go across.
Okay, that makes sense. What about going down?
Second, down a group. From top to bottom, atomic radius increases regularly.
Gets bigger going down. Why this time?
Here, as you move down, the principal quantum number n increases. This means that new electron shells are being added, and the valence electrons are located in shells that are progressively further and further away from the nucleus. Distance increases significantly.
Adding whole new layers.
Right, adding whole new layers or shells. Additionally, the inner energy levels are filling up with electrons, and these inner electrons provide increased shielding of the outer valence electrons from the full attractive pull of the nucleus. Think of adding more blocking layers between the magnet and the outer electron.
More shells, more shielding.
Yes. This increased distance and increased shielding effect significantly outweigh the increasing nuclear charge, more protons, leading to a larger atomic size as you descend the group. It's a clear and consistent trend. Noble gases can sometimes seem like an exception in tables because their radii are often measured differently. Van der Waals radius, which measures non-bonded atoms, making them appear larger than halogens, but the general group trend holds.
That explanation of atomic radius, especially linking it back to 0 by E20 by 820 by 910 by E20 by 820 by 91 and shielding, is incredibly clear. Now, what about ionic radius? How does an atom size dramatically change when it forms an ion, whether by gaining or losing electrons?
This is a crucial distinction and quite straightforward once you understand the electron-proton balance. When an atom loses electrons to form a positive ion or a cation.
Like Na becoming Na-O.
Exactly. The cation is always smaller than its parent neutral atom. The reason is simple. One or more electrons have been removed, but the nuclear charge, the number of positive protons pulling inwards, remains exactly the same.
Same pull, fewer electrons being pulled.
Precisely. With fewer electrons now experiencing that same nuclear pull, the remaining electrons are drawn closer to the nucleus. The effective pull on each electron increases and the overall electron cloud shrinks. For example, a neutral sodium atom, Na, has an atomic radius of about 186 pm, but when it loses one electron to become the Na ion, its ionic radius shrinks significantly to just 95 pm.
Big difference. What about gaining electrons?
Conversely, when an atom gains electrons to form a negative ion or an anion,
like F becoming F.
Perfect example. The anion is always larger than its parent neutral atom. When an electron is added, it increases the electron repulsion within the existing electron cloud. You're adding more negative charge into the same general space.
More electrons pushing each other apart.
Exactly. This increased repulsion, combined with the fact that the same nuclear charge is now trying to hold on to more electrons, so the effective pull per electron decreases slightly, causes the electron cloud to expand. For instance, a neutral fluorine atom has an atomic radius of about 64 pm, but when it gains one electron to become the S ion, its ionic radius expands considerably to 136 pm.
Also a big difference, but in the other direction.
Right. This concept also beautifully explains the sizes of isoelectronic species.
Isoelectronic, meaning same number of electrons.
Yes, exactly. These are atoms and ions that have the exact same number of electrons. A common example series includes OS, F, Mo, Ne, Naho, and the Y, all of which have 10 electrons, the same configuration as neon.
Okay, all have 10 electrons. Are they the same size then?
No, not at all. Despite having the same number of electrons, their radii will be distinctly different because their nuclear charges the number of protons pulling on those 10 electrons very significantly. Oxygen has 8 protons, fluorine 9, neon 10, sodium 11, magnesium 12.
Ah, so the magnet strength is different.
Precisely. The ation with a greater positive charge, like Mgol-Balesho with plus 12 pull, will have the smaller radius because its nucleus exerts a stronger attractive pull on the same 10 electrons. Conversely, the anion with the greater negative charge, like Mgu with only plus 8 pull on 10 electrons, plus more repulsion, will have the larger radius because the increased electron repulsion slightly outweighs the weaker nuclear pull per electron, causing the electron cloud to expand further.
So for that series, Ngo smallest, then Neo, Nekovuru, and O largest.
Got it. Perfect. So if you were asked to compare, say, neutral Mg, Mgr ion, neutral Al, and Lr ion, think about protons versus electrons.
Okay. Mlu has 12p, 12e, Mbol has 12p, 10e, Al has 13p, 13e, L has 13p, 10e.
Right.
So the largest would be the neutral atom with more electron shells, which is Al, Ne3 shell, slightly smaller than Mg, Ne3 shell, but less Zeph. Actually, Mg is larger than Al across the period, so Mg is largest.
Good correction. M is largest.
Then Al. Then comparing the ions, both have 10 electrons. Alo has more protons, 13, pulling on those 10 electrons, than Mg, 12 protons, so Alo must be the smallest.
Excellent reasoning. Largest is Mg, then Al, then Mj, and the smallest is Lo. Perfect application of the principles.
Great. So we've explored the physical size of atoms and ions. Now let's shift our focus to the energy involved in removing an electron from an atom. What exactly is ionization enthalpy, and why is it such an important indicator of an element's reactivity?
Ionization enthalpy, often denoted as L, or sometimes IE, is a crucial connotative measure of an element's inherent tendency to lose an electron. More formally, it's defined as the minimum energy required to remove the most loosely bound electron from 1 mole of isolated gaseous atoms in their ground electronic state.
Okay, energy to pull off the easiest electron. Why isolated gaseous atoms?
Good question. We specify isolated gaseous atom in its ground state to ensure we're measuring the property of the atom itself, totally free from any interactions with other atoms, like in a solid or liquid, and making sure the electron isn't already partway out in an excited state. This allows for a fair and consistent comparison between different elements.
Makes sense. Purely the atom's hold on its electron.
Exactly. When we talk about removing the very first electron, we call it the first ionization enthalpy, represented as Xg plus E. If we then remove a second electron from the already formed positive ion, that's the second ionization enthalpy plus E, and so on for third, fourth, etc.
And it gets harder each time.
Always. A fundamental point to remember is that energy is always required to remove electrons from an atom because you're overcoming the attractive electrostatic force of the positive nucleus. Therefore, ionization enthalpies are always positive values, indicating an endothermic process energy must be put in.
You have to pay energy to remove an electron.
Right. And it's always harder, requires more energy, to remove an electron from an already positively charged ion than from a neutral atom. Why? Because now that same positive nucleus is pulling on fewer electrons, so its hold on each remaining electron is stronger. That's why the second ionization enthalpy, i.e. error, is always significantly higher than the first, i.e. arrow, and the third, i.e. is higher still, and so on. It gets progressively much harder.
Given that energy is always required, what are the general trends for ionization enthalpy as we move across the periodic table and down a group? Do they follow the same logic as atomic radius, maybe in reverse?
Generally, yes. They're inversely related to atomic radius trends, and the logic follows directly from effective nuclear charge and shielding. There are two clear and predictable trends for the first ionization enthalpy. First, across a period from left to right, the first ionization enthalpy generally increases.
Harder to remove an electron going across.
This is because, as we discussed with atomic radius, moving across a period means the atomic number increases, leading to an increased effective nuclear charge. Z0 by E20 by 820 by 9 by E20 by E20 by 820 by 91. Simultaneously, the atomic radius generally decreases. Both factors mean the outermost electrons are held more tightly by the nucleus, Consequently, it requires significantly more energy to overcome that stronger attraction and remove one of those electrons.
Tighter grip needs more energy to break. Makes sense.
Exactly. Second, down a group from top to bottom, the first ionization enthalpy generally decreases.
Easier to remove an electron going down.
Yes. As we move down a group, the outermost electron is in a higher principal quantum shell, larger n, meaning it's progressively further away from the nucleus. There's also an increased shielding effect from the larger number of inner electrons, which more effectively screens the valence electron from the full attractive pull of the nucleus. This combination of increased distance and more effective shielding significantly outweighs the increasing nuclear charge, making it easier to remove the outermost electron, thus requiring less energy.
Further away, more shielded, easier to pluck off.
You got it. That's the essence of the trend down a group.
Okay, but I remember seeing some anomalies or unexpected little wiggles in the data for ionization enthalpy, especially in the p block, where the general trend seems to break slightly. This is where it gets really interesting for me, as it hints at the subtle nuances of electron configurations and stability. What's going on there?
You've hit on a crucial point. These anomalies or deviations are where the simple trends give way to the complex, beautiful reality of quantum mechanics and electron configurations. They are absolutely key to understanding the subtle interplay of orbital shapes, electron repulsion, and the special stability associated with certain electron arrangements. Let's look at two prominent examples from the second period, which often cause confusion.
Okay, let's break them down.
First, if you compare beryllium, group 2, Z4, and boron, group 13, Z5, based on the general trend of increasing IE across a period, boron, having a greater nuclear charge, +5 versus +4, should have a higher first ionization enthalpy than beryllium.
Right, that's what the trend predicts.
However, experimentally, beryllium actually has a higher first ionization enthalpy than boron. It's flipped. Why? Let's take this step by step.
Look at their electron configurations. Beryllium is free S2SES SECO. Boron is ferron SET2SET no P.
Okay.
Second part. In beryllium, the electron being removed is from a filled 2s orbital. In boron, the electron being removed is the single electron from a 2p orbital.
Removing 2s versus 2p.
Third part. Now, remember orbital shapes and penetration. A 2s electron, being spherical, penetrates closer to the nucleus on average and is more strongly attracted than a 2p electron, which has that dumbbell shape and lobes further out. Also, the 2p electron in boron is slightly more shielded from the nucleus by the inner 2s electrons compared to how the 2s electrons shield each other in beryllium.
So the 2s is held tighter than the 2p.
Generally, yes, within the same shell. And removing an electron from a filled orbital, like in Beer, requires more energy than removing the first single electron from a p-orbital, like in B.
Therefore, it is surprisingly easier, requires less energy, to remove the 2p electron from boron than it is to remove a more tightly held 2p electron from beryllium, causing this inversion in the trend, IE of B, IU of B.
Wow, okay, subtle orbital effects matter. What's the other famous anomaly?
The other classic anomaly is observed between nitrogen, group 15 Z7, and oxygen, group 16 Z8. Again, based on the trend, oxygen Z8 should have a higher first ionization enthalpy than nitrogen Z6.
Oh, it doesn't.
Correct. Nitrogen's first IE is actually higher than oxygen's. Let's break this one down too, focusing on electron configuration stability.
Nitrogen's configuration is Gronlax 3O2S SIP2PAO. Oxygen's is 1-Lax2SE2PO.
Okay, 2POs versus 2PO.
Second part, think about how electrons fill the p orbitals. Remember, Hund's rule, fill singly first. Nitrogen has a remarkably stable, half-filled 2p subshell. It has exactly one electron in each of the three p orbitals, p0 by 10, ISB50 by A7As, p0 by E10, ISB50 by A7As, all with parallel spins. This half-filled configuration has extra stability.
Half-filled shells are stable. Got it.
Third part. Now look at oxygen, 2PO. To fit the fourth electron, one of the 2p orbitals must now contain two electrons with opposite spins, say PPOA10, ISB50 by A7, P0 by E10, ISB50 by A8. This means there's an electron pair in one orbital.
Putting two electrons in the same small space.
Exactly. This pairing results in increased electron repulsion within that specific orbital. Imagine two negatively charged electrons being forced to occupy the same small region of space. They push each other away.
This repulsion makes it slightly easier to remove that fourth 2p electron from oxygen, because removing it relieves this repulsive strain and leaves behind a stable half-filled configuration, like nitrogen's. Removing an electron from nitrogen's already stable half-filled configuration disrupts that stability, requiring more energy. So IEO of N, IEO of O. These exceptions perfectly illustrate the crucial interplay of orbital penetration, electron-electron repulsion, and the inherent extra stability of half-filled or fully filled electron subshells. It's pure quantum mechanics in action.
That's a fantastic explanation of those subtle but crucial exceptions. It really shows it's not just about simple trends. Okay, so if ionization enthalpy is about the energy needed to lose an electron, what's the flip side when an atom gains an electron? What is that property called, and what does it tell us about an element's tendency to form negative ions?
That's called electron gain enthalpy, denoted as AEEH, or sometimes EA, electron affinity, though technically enthalpy is more precise. It's defined as the enthalpy change that occurs when an electron is added to 1 mole of neutral gaseous atoms to convert them into negative ions. So the process is Xg plus E ental G.
Energy change when gaining an electron, is it always positive like ionization enthalpy?
No, and that's a key difference. Unlike ionization enthalpy, which is always positive because energy is required to remove an electron, the process of adding an electron can be either exothermic, meaning energy is released, resulting in a negative AEH value, or endothermic, meaning energy must be absorbed or put in, resulting in a positive EEH value.
So some atoms release energy when they gain an electron, others need energy pushed onto them.
Exactly. It depends on the atom's electron configuration and how stable the resulting anion is.
So which elements are typically eager to gain an electron and release energy, negative here-ish, and which ones would actually require energy input, positive here-ish, to force an electron upon them?
Elements that have a strong affinity or hunger for electrons will release energy upon gaining one, leading to a highly negative electron gain enthalpy. A prime example is group 17, the halogens, like fluorine or chlorine. They have very high negative electron gain enthalpies, meaning the process is very exothermic.
Why are they so eager?
Because gaining just one electron allows them to achieve that very stable, completely filled noble gas electronic configuration. In sulfur and UCO, they are effectively just one electron short, so completing the shell is energetically very favorable. They release a lot of energy doing it.
Makes sense. What about elements that don't want electrons?
On the complete other end of the spectrum, noble gases, group 18, with their already stable, completely filled valence shells, have large positive electron gain enthalpies. If you try to force an electron onto a noble gas atom, it would have to enter the next, much higher energy, unoccupied principal quantum level. For example, for neon, NBL2 is full, the electron would have to go into NBL3. This creates a very unstable electronic configuration.
Like putting furniture in the attic when the house is full.
Good analogy. It requires significant energy input to make that happen, making the process highly endothermic. Positive Yori-Yori-Yoch. They simply don't want any more electrons. Elements like the alkaline earth metals, group 2, also tend to have positive or only slightly negative values because the incoming electron would have to go into a higher energy orbital, disrupting the stable filled s orbital.
Okay. What are the general trends for electron gain enthalpy across a period and down a group? Do they follow a similar pattern to ionization enthalpy, or are there differences?
Generally, they do follow related patterns. But remember, we're talking about becoming more negative, more energy released, or less negative, less energy released, or even positive. Across a period, from left to right, the electron gain enthalpy typically becomes more negative.
So easier to gain an electron going across?
Generally, yes, or rather, more energy is released.
Yeah.
As the effective nuclear charge, 0 by E20 on by 20, by 910, by E20, by 820, by 91, increases, and the atomic size decreases across a period, it becomes progressively easier for the nucleus to attract and accommodate an incoming electron. The added electron is closer to the positively charged nucleus and experiences a stronger attraction, leading to a greater release of energy upon its addition. More negative U's. Halogens, group 17, are the peak here.
Okay. And down a group?
Down a group, from top to bottom, the electron gain enthalpy generally becomes less negative.
Harder to gain an electron going down, or less energy released?
Less energy released, generally. As you move down a group, the atomic size increases significantly. This means the added electron will be entering a shell that's further away from the nucleus and will experience less attraction. Additionally, the increased shielding from the core electrons further reduces the effective nuclear charge felt by the incoming electron. Both factors make it energetically less favorable for an electron to be added compared to smaller atoms higher up in the group. This leads to a less negative, smaller release of energy, or sometimes even positive electron gain enthalpy further down.
Interesting. But wait, you mentioned earlier something about oxygen or fluorine having less negative electron gain enthalpies than sulfur or chlorine below them. That seems to directly contradict the trend you just described for going down a group. Is this another one of those anomalies caused by the specific nature of electron shells?
Yes, absolutely. You remembered that correctly. And it is a very important exception to the general trend down a group. It's another excellent example where subtle atomic effects related to size become dominant. It is counterintuitive because fluorine is smaller and more electronegative, so you'd expect it to attract an electron more strongly than chlorine.
Right. So why is chlorine's electron gain enthalpy more negative, more exothermic?
The explanation, again, lies in the extremely small size of the atoms in the second period, like O and F, compared to the third period, like S and Cl. Let's break this down.
When an electron is added to oxygen or fluorine, it has to go into the relatively small, compact angle-2 quantum level.
The second shell.
Second part. This small space in the NLU shell means that the incoming electron experiences significant electron repulsion from the other electrons already crowded into that compact shell. Imagine trying to squeeze one more person into an already very crowded small room. Lots of jostling and discomfort.
Okay, strong repulsion in the small shell.
Third part. Now, for sulfur or chlorine in the third period, the incoming electron goes into the larger NQ3 quantum level. There is significantly more space available in the NQ3 shell compared to the NQ2F.
More room in the third shell.
Result. This larger available space means the electron repulsion experienced by the incoming electron is much less severe in S or Cl compared to O or F. Even though the nucleus might be slightly less effective at pulling it in due to distance shielding, the dramatically reduced repulsion in the larger shell makes the overall process more energetically favorable, more exothermic, more negative AGH for chlorine and sulfur compared to fluorine and oxygen. This again beautifully demonstrates how atomic size and electron repulsion effects can sometimes override the simpler trends based purely on Z0 radii by 820 by 910 for 5820 by 20 by 910 by E2A by 820 by 91 or electronegativity. It's a crucial subtlety for elements in the second period.
That makes sense. The crowding effect is more important for the small ones.
Okay,
finally, let's look at electronegativity. How is it different from electron gain enthalpy, which sounds quite similar, and why is it such an important concept in understanding how atoms actually bond together to form molecules?
That's a common point of confusion, but the distinction is critical. While electron gain enthalpy is a precise, measurable energy change describing an isolated gaseous atom's tendency to gain a single electron to become an anion.
Energy for X plus EX, right?
Right. Electronegativity is distinctly different. It is a qualitative measure, meaning it's not a directly measured energy value, but rather a calculated or assigned relative value of an atom's ability to attract shared electrons towards itself when it is part of a chemical bond within a molecule or compound.
So it's about pulling on electrons in a bond, not gaining one completely.
Exactly. It's about its pulling power or electron greediness within a shared covalent bond. It reflects how strongly an atom competes for the electrons it's sharing with another atom. Various numerical scales have been developed to quantify it, with the Pauling scale being the most widely used and the one you usually see. Linus Pauling arbitrarily assigned fluorine, which is famously the most electronegative element. It has the strongest pull on shared electrons, a value of 4.0, and all other elements are scaled relative to that.
Okay, so it's a relative scale of pulling power in bonds with fluorine at the top. What are the trends for electronegativity across a period and down a group? Do they generally follow the patterns we've seen for ionization enthalpy?
Yes, the trends for electronegativity mirror those of ionization enthalpy quite closely, and for the same underlying reasons related to Z by E20 by OE20 by 910 by E9 by NE20 by A20 by 91, and atomic size. Across a period from left to right, electronegativity generally increases.
Stronger pull going across.
Yes. As the atomic radius decreases and the effective nuclear charge, Z0 by E20 by 820 by 910 by 820 by 820 by 91, increases across a period, the nucleus's attractive force on its own outer electrons becomes stronger. Consequently, its ability to attract the shared electrons in a covalent bond also becomes significantly stronger. The atom's ability to pull those shared electrons towards itself increases. Fluorine, top right, ignoring noble gases, is the peak.
Okay, and down a group.
Down a group, from top to bottom, electronegativity generally decreases.
Weaker pull going down.
Correct. This is primarily due to the significant increase in atomic radii and the increased shielding effect from the inner electrons. As the valence electrons involved in bonding are further from the nucleus and more effectively shielded from its positive pull, the nucleus's ability to attract shared electrons in a bond is significantly reduced. Francium, bottom left, would be the least electronegative.
So diagonally from bottom left to top right, electronegativity increases.
That's a great way to visualize the overall trend. This concept of electronegativity is incredibly crucial because it helps us predict the very nature of the chemical bond formed between two atoms. For example, if two atoms with a large difference in electronegativity bond, like sodium and chlorine, the more electronegative atom, Cl, pulls the shared electrons so strongly that it essentially captures them, forming an ionic bond, ni-mo-clo. If the electronegativity difference is small, like between two carbon atoms or carbon and hydrogen, the electrons are shared more equally, resulting in a covalent bond. Differences in between led to polar covalent bonds, where electrons are shared unequally.
So it predicts bond type.
Yes, and bond polarity. There's also a direct relationship. Electronegativity is directly related to nonmetallic properties, the tendency to attract or gain electrons. Conversely, it's inversely related to metallic properties, the tendency to lose electrons. So, increasing electronegativity across a period correlates with increasing nonmetallic character, and decreasing electronegativity down a group correlates with increasing metallic character. It's a powerful, quick indicator of an element's fundamental chemical nature just by looking at its position and its relative electronegativity value.
Now that we understand these fundamental physical trends, how atomic size, ionization enthalpy, electron gain enthalpy, and electronegativity change across the table, how do these translate into an element's actual chemical behavior? Let's start with concepts like valence and oxidation states, which are central to how elements form compounds.
Right. The valence of an element, especially for the representative or main group elements, S and P blocks, is a very characteristic property and can often be directly predicted from their group number, which relates to their valence electronic configurations. Generally, the valence is equal to the number of electrons in their outermost shell, like group 1 is valence 1, group 2 is 2, group 13 is 3, group 14 is 4.
Or sometimes 8 minus the group number.
Exactly. For groups 15, 16, 17, their common valence is often 8 minus the number of valence electrons. For example, group 17 has 7 valence electrons, 8, 7, 1, common valence is 1. Group 16 has 6, 8, 6 to 2, common valence 2. This elegantly explains why elements in the same group tend to exhibit similar valencies and therefore form compounds with similar chemical formulas and bonding patterns. For example, NaCl, KCl, LCl, or HEO, HS.
Okay, valence relates to group number. What about oxidation state? Is it the same thing?
Nowadays, we frequently use the term oxidation state or oxidation number, which is closely related to valence, but is a more formal and versatile concept, especially for transition metals or complex compounds. The oxidation state is the hypothetical charge an atom would have in a molecular ion if all the bonds to atoms of different elements were 100% ionic. It's assigned based on a set of rules, mainly considering electronegativity differences.
So it's like a formal charge based on who wins the electrons in the bond.
That's a good way to think about it. Let's take those two examples again. OF Euro and NeO. In OF, fluorine is the most electronegative element, so it always wins the electrons and gets an oxidation state of -1. Since there are two fluorines, oxygen must have an oxidation state of +2 to make the molecule neutral. Here, oxygen is +2.
Even though oxygen usually likes to be negative?
Yes, because fluorine is even more electronegative, but in NeO, oxygen is much more electronegative than sodium, so oxygen wins the electrons and takes its usual oxidation state of -2. Each sodium atom, being less electronegative, loses an electron and has an oxidation state of +1. This concept is incredibly powerful for tracking electron transfer in redox reactions and for predicting the correct formulas of countless ionic and covalent compounds like Cyber, silicon group 14, often +4, bromine group 17, usually -1, or aluminium group 13, usually +3, sulfur group 16, usually -2.
That makes perfect sense. But what if the anomalous properties of second period elements? We often hear that elements like lithium and beryllium, or even carbon, nitrogen, oxygen, fluorine, behave somewhat differently, almost uniquely, from the other members further down in their own group. Why is that? What makes them the chemical odd ones out in their families?
This is a fantastic point, and it's where atomic structure, specifically the unique properties of the NO2 shell, truly explains significant deviations from general group trends. The first element of each main group, so lithium in group 1, beryllium in group 2, and then boron through fluorine in groups 13, 17, often differ significantly in many respects from the heavier members, congeners below them in their respective groups.
How do they differ? Give me an example.
For instance, lithium, unlike other alkali metals, Na, K, etc., and beryllium, unlike other alkaline earth metals, and Mg, Ka, etc., form compounds with a much more pronounced covalent character. They tend to share electrons rather than forming purely ionic bonds. In contrast, the other, heavier members of these groups primarily form clear-cut ionic compounds, like NaCl, MgCl.
Interesting. Li and B are more covalent.
Yes. In fact, lithium's chemical behavior is often more similar to magnesium, the element diagonally below it to the right, and beryllium's chemistry resembles aluminium's, also diagonal. This interesting phenomenon is commonly referred to as a diagonal relationship across the periodic table. LiMg, Bl, BSi.
Diagonal relationships. Why exactly do these particular lighter elements show these unique, sometimes anomalous behaviors, and why that diagonal similarity? Is it all tied back to their fundamental atomic structure?
It absolutely boils down to their fundamental atomic structure and the consequences of being in that second period, N2. There are three main factors usually cited. First, their exceptionally small atomic and ionic size. They're much smaller than any other elements in their respective groups. Second, a direct consequence of that small size combined with their nuclear charge is their large charge-to-radius ratio. This high charge density influences their bonding. And third, their generally high electronegativity compared to other members further down in their groups. These combined factors contribute significantly to their greater tendency to form covalent bonds. High electronegativity, high charge density polarizes electron clouds, and exhibit unique reactivity patterns that often resemble the element diagonally below them, which happens to have a similar charge-to-radius ratio.
So small size, high charge density, high electronegativity. Any other factors?
Yes, there's one more crucial difference related to their available orbitals. The first member of a group in the S and P blocks only has valence electrons in the N2 shell. This shell contains only 4 valence orbitals, 1 2s orbital and 3 2p orbitals.
Just S and P.
Right. This fundamentally limits their maximum covalency, the maximum number of covalent bonds they can typically form, to 4, because they only have 4 orbitals available for bonding. For example, boron can form a species like BF arrow, 4 bonds, but it cannot form BF here.
Can't make 6 bonds if you only have 4 orbitals.
Exactly. Later members in the same groups from period 3 onwards, however, have valence electrons in shells, N3, 4, etc., that include not only s and peak orbitals, but also emptied orbitals like 3s, 3p, and crucially, 5 empty 3 orbitals in the NT3 case. These available orbitals allow them to expand their valence shell or octet to accommodate more than 4 pairs of electrons in bonding.
They can use the orbitals for extra bonds.
Precisely. A classic example is aluminium, in the same group as boron, but period 3. Aluminium can form a complex ion like alpha-ferro, where its covalency is 6, utilizing its third orbitals. Phosphorus can form PCl Euros, sulfur SFer, etc. This ability to expand the octet is unavailable to second period elements.
It's a huge difference in bonding capability.
It is. Furthermore, the second period p-block elements, CNO, show a much greater ability to form strong pup multiple bonds, double and triple bonds to themselves, like carbon double or triple bonds, CaVAC, or nitrogen triple bonds, NN, and to other second period elements like carbon-oxygen double bonds, COO, carbon-nitrogen triple bonds, CAN. Their small size allows for effective sideways overlap of orbitals.
Like in organic chemistry.
Exactly. It's fundamental to organic chemistry. This ability to form strong multiple bonds is significantly less common or results in weaker bonds for the heavier elements in the same group, like Psi, PS, which prefer forming networks of single bonds due to their larger size and less effective p-orbital overlap. These are the key underlying structural reasons for their unique, sometimes surprising chemistry compared to their heavier relatives.
That brings it all together beautifully. It's not just trends, but understanding the exceptions based on structure. So how do all these properties, the atomization radii, ionization enthalpy, electron gain enthalpy, and electronegativity, plus these second period effects ultimately tie into an element's overall chemical reactivity? How can we use the periodic table to quickly gauge how reactive an element will be, or even the type of compounds it might form, like acidic or basic oxides?
This is where all the trends beautifully converge, giving the periodic table its immense predictive power regarding chemical behavior. The periodicity in these fundamental atomic properties directly dictates an element's chemical reactivity. Elements located on the extreme left of a period, such as the alkali metals in group 1, have the lowest ionization enthalpies.
Easiest to lose electrons.
Exactly. This means they readily lose their outermost electron to form positive ions, making them highly reactive metals. They act as powerful reducing agents in chemical reactions because they're eager to give away electrons. Their reactivity generally increases down the group as IE decreases.
Okay, left side, reactive metals reducing agents. What about the right?
Conversely, elements on the extreme right of a period, specifically the halogens in group 17, we exclude the noble gases here, which are largely unreactive, have the highest negative electron gain enthalpies.
Most eager to gain electrons.
Right. This means they readily gain an electron to form negative ions, anions, achieving that stable noble gas configuration. This makes them highly reactive nonmetals. They act as powerful oxidizing agents in chemical reactions because they are eager to accept electrons from other species. Their reactivity generally decreases down the group as electron affinity becomes less negative and size increases.
So right side, halogens, reactive nonmetals, oxidizing agents.
Precisely.
So it sounds like reactivity is actually highest at the two extremes of the periodic table, the far left and the far right, and then it generally becomes much lower as you move towards the center. Is that the takeaway?
Precisely. That's a great summary. Chemical reactivity tends to be highest at the two ends of a period, the highly metallic alkali metals on the left and the highly nonmetallic halogens on the right, and generally lowest towards the center of the table, particularly among the transition metals and the metalloids or central p-block elements.
And this connects to metallic-nonmetallic character, too.
Absolutely. The metallic character, tendency to lose electrons, form basic oxides, is highest on the extreme left and predictably decreases as you move across the period from left to right. Simultaneously, the non-metallic character, tendency to gain electrons, form acidic oxides, increases across the period.
How does this show up in their oxides?
This fundamental shift is wonderfully reflected in the acid-base nature of their oxides. Elements on the extreme left, like Na, K, Ka, form highly basic oxides, where G, sodium oxide, NaOH, or calcium oxide, CaO. These are ionic oxides that react vigorously with water to form strong bases, like sodium hydroxide, NaOH, or calcium hydroxide, CalOH.
Metal oxides are basic.
Generally, yes, especially for the reactive S-block metals. As you move to the extreme right, the nonmetals, like ClSN, form highly acidic oxides, Ag dichlorine heptoxide, kilillier sulfur trioxide, X sulfur trioxide, LaOH, nitrogen pentoxide, NeOO. These are typically covalent oxides that react with water to form strong acids, like perchloric acid, HClOO, sulfuric acid, HSO, or nitric acid, HNO.
Non-metal oxides are acidic.
Generally, yes. And elements in the center of the table, particularly the metalloids or some less metallic p-block elements like aluminium or zinc, tend to form amphoteric oxides.
Amphoteric, meaning both.
Exactly. They can behave as both acidic, reacting with bases, and basic, reacting with acids. Aluminium oxide, Al-Acero, and zinc oxide, ZNO, are classic examples. Some oxides in the middle, like carbon monoxide, the CO, or nitric oxide, NO, or nitrous oxide, NNO, are essentially neutral. They don't show significant acidic or basic properties in water, so you see a complete spectrum of reactivity and acid-based behavior across the table, all neatly explained and predicted by the element's position and its underlying electronic properties.
Wow, that was a truly comprehensive deep dive into the periodic table. We really covered a lot of ground. We started by exploring the sheer necessity for such a system, moving from that chaos of discovery towards order.
Right, the need for a map.
We then journeyed through its remarkable historical development, from Dobereiner's early triads and Newland's intriguing law of octaves, right up to the bold predictions and genius of Mendeleev, a true scientific visionary who dared to leave gaps and even correct the data based on his chemical intuition.
His predictive power was key.
Then we saw how Moseley's groundbreaking work with X-ray spectra completely redefined the table based on atomic number, leading us to the modern long form we use today, and even tackling the systematic naming of those fleeting, super-heavy elements.
Shifting from mass to number was fundamental.
And we broke down the different blocks S, P, D, and F, each defined by where that last electron lands, which dictates so much about their behavior.
Yeah, linking configuration directly to the blocks.
And you've shown us how the modern periodic law, fundamentally rooted in our understanding of electronic configurations, helps us decode all those predictable patterns, those trends, and the element's properties.
Exactly. We saw how atomic radii consistently decrease across a period but increase down a group, driven by zeros Bach E20 by 820, by 910 Bach 820 by 820 by 91, and shielding.
Right. And how ionization, enthalpy, and electronegativity generally do the opposite, increasing across a period and decreasing down a group, reflecting how tightly electrons are held or attracted.
Mm-hmm. And how electron gain enthalpy generally becomes more negative across a period, more energy release, but less negative down a group, with those interesting exceptions for the second period due to electron repulsion in small shells.
Yes. Those anomalies were fascinating.
We even touched upon the unique, sometimes anomalous behavior of those second period elements, their small size, high electronegativity, lack of d orbitals, and ability to form multiple bonds, and how all these fundamental atomic properties ultimately dictate an element's overall chemical reactivity and the very nature of the compounds it forms, including the acid-base properties of their oxides. It truly is a complete and coherent picture, all held within that simple-looking chart.
It really is. And it all comes back to this incredible ability to predict and understand how the fundamental building blocks of our world interact, from the tiniest atoms to the vast array of compounds they form that make up everything around us. For you, our curious listener, what's the most profound takeaway from this entire journey through the elements that you hope they internalize and maybe use?
For you, the learner, the most crucial takeaway I hope you grasp is this. The periodic table isn't merely a chart to memorize facts from. It is an incredibly powerful, highly organized, and fundamentally predictive tool. The true beauty and utility of it lies in its ability to condense a massive amount of complex chemical information into a logical, accessible framework. As you continue your studies, don't just look at it as static boxes. Try to actively visualize how factors like effective nuclear charge pulling inwards and electron shielding pushing outwards influence these trends across and down the table.
Make it dynamic in your mind.
Exactly. When you look at an element's position, let it immediately trigger an anticipation of its general size, its tendency to lose or gain electrons, its IE and EA, its pulling power in bonds, electronegativity, and its likely reactivity. Think about why it behaves that way based on its electron structure. Can you predict the formula of its oxide? Will it be acidic or basic? Can you compare its reactivity to its neighbors? This kind of active engagement using the table as a think-out tool is far more valuable than rote memorization. Imagine being able to roughly design a new material, predicting its properties even before trying to make it, just by understanding the trends on this chart. That's the real magic and the predictive power we want you to harness. Keep exploring, keep questioning, and continue to delve deep into the endlessly fascinating world of chemistry revealed by the periodic table.